Imagine the early universe, a time when stars, star clusters, galaxies, and even quasars with gargantuan black holes were just beginning to form. But wait, there's a question that has long puzzled scientists. How did these ultramassive black holes come into existence in such a short span of time? Observations by the Chandra X-ray Observatory have started to unravel this enigma. By studying a tiny region of the sky, astrophysicists have discovered numerous active supermassive black holes. But here's the twist. The formation of the first stars played a pivotal role in the birth of these supermassive black holes. These primordial stars were colossal, much larger than those we see today, collapsing and heating up faster, leading to the creation of black holes without a supernova explosion. But that's not all. There's another ingredient in this cosmic recipe. Do you know what that might be? Let's leave that for a bit later. What's up, my amazing and curious folks? Ready to unravel mysteries together? I'm your host, Caesar, and I'm here with the profoundly insightful Sonia. Are you ready to dive into the cosmic abyss with us today, Sonia?
Hi everyone, this is Sonia Guimaraes here, and I'm absolutely thrilled to embark on this journey of discovery with all of you.
Before we dive in, make sure you're subscribed to our channel and have hit that bell icon to stay updated. Remember, we're on the Curiosity Wonderland every day, unraveling the mysteries of the universe together. Buckle up, folks. This ride's going to be a thrill. Okay, let's start this cosmic journey by imagining the early universe. Guys, picture this. A place with no planets, stars, or galaxies. It was uniform, free of the diverse celestial bodies we see in today's cosmos. But as we look back, even to when the universe was just a few 100 million years old, we find a fascinating array of objects. Stars and star clusters were in abundance, galaxies lighting up the universe, and even quasars with enormous black holes were forming. And now we're left with the classic chicken and egg conundrum. How did these ultramassive black holes form in such a short period, given that there's a maximum rate at which black holes can grow? We've been pondering over this for decades, but thanks to the Chandra X-ray Observatory, we've started to get some answers. With hundreds of hours of observations of one region of the sky, scientists have discovered hundreds of active supermassive black holes. X-ray observatories, not to be underestimated, have proven to be highly sensitive to the presence of active black holes. But let's take a step back and head to the time just 50 to 100 million years after the Big Bang. This is when the very first stars began to form from massive gas clouds. These clouds, composed solely of hydrogen and helium, struggled to radiate heat away and dissipate their energy. As a result, the clumps that formed and grew needed to be much more massive than those forming stars today. This, my friends, had significant implications for the types of stars that formed and the astrophysical processes that occurred alongside their formation. Today, we typically form stars that are about 40% the mass of the Sun. But back then, the first stars were about 25 times more massive on average. These behemoths were born out of streams of gas which needed to cool to collapse. So the largest, most massive clumps were the ones forming stars early on. But you may ask, how does this all connect to the formation of supermassive black holes? Well, hold on to your seats as we delve deeper into this cosmic mystery.
This reminds me of a time from my childhood. You know, I was always intrigued by the night sky and celestial bodies. I remember this one time when I was around 10 years old. I asked my dad how stars were born. Being a science teacher himself, he took the time to explain to me how stars formed from clouds of gas and dust. But he remarked that there was still a lot we didn't know about the universe, especially about the earliest stars and black holes. That conversation sparked a sense of wonder in me, and from then on, I fell in love with the mysteries of the cosmos. But back to our topic, let's delve deeper into the formation of the early universe's massive celestial bodies. The average first star might have been as much as 10 times the mass of our Sun, with some stars reaching hundreds or even thousands of solar masses. Just imagine a star thousands of times bigger than our Sun. And it gets more fascinating. Supercomputer simulations of cosmic evolution show clumps of matter growing to possess individual stars containing tens of thousands of solar masses, each in just over 1 million years. This rapid growth could provide the seeds for the universe's earliest and most massive black holes, and also pave the way for the development of galactic structures. But there's a long-standing tension in cosmology between what's expected and what's observed. Some scientists postulate that the black holes at the centers of galaxies are formed from the mergers and growth of stellar remnants alone. Others believe in different mechanisms, like the formation of primordial black holes that the universe was born with, or the formation of large seed black holes that arise independently of stars and stellar cataclysms. But let's consider the from stars and stellar remnants alone route. Most of the first-generation stars would end their life in a supernova, leading to either a neutron star or a small, low-mass black hole. But there's another fascinating aspect to consider. The most massive stars, devoid of any heavy elements, can reach such high core temperatures that photons can become so energetic that they start producing matter and antimatter pairs from pure energy alone. This is a critical application of Einstein's E equals mc squared. If temperatures are high enough, photons can create an electron-positron pair. This happens in some of the most massive stars even today. When high enough energy photons are produced, they cause a pressure drop and a runaway reaction that destroys the star. This complex, intriguing process offers a glimpse into the enormous energy and transformative processes that birthed the early universe's celestial bodies.
So let's talk about a particular event known as a pair instability supernova. This occurs in ultramassive stars. Like all stars, gravitation is pulling all of the matter in towards the star's center, while the radiation produced in the cores of these stars pushes back, holding the star up and preventing its collapse. This happens regardless of the star's mass, as a balance point must always be reached in any object that isn't going to vary, oscillate, collapse, or explode. However, in these ultramassive stars, the radiation pressure and temperatures are higher and more high-energy processes occur, including one known as pair production. This is when photons start producing electron-positron pairs. The production of these pairs causes some of the radiation pressure to drop. Photons, which move at the speed of light, exert a greater amount of outward pressure than slower-moving massive particles. When a star reaches a temperature high enough to produce these electron-positrons pairs, its ability to hold itself up against gravitational collapse is depleted.
So what happens when a star can no longer hold itself up against the forces of gravity?
Good question. Well, there are a few narrow mass ranges where the star would actually destroy itself completely, but a large fraction of cases will result in the entire star collapsing directly to form a black hole. This is called the direct collapse scenario.
Can you give us an example of this direct collapse scenario?
Absolutely. There have been a few observed instances even in the late-time universe. One notable example comes from photos from Hubble showing a massive star, about 25 times the mass of the Sun, that simply disappeared with no supernova or other explanation. The only reasonable candidate explanation is direct collapse. This is a significant step, my friends. It implies that the most massive stars of all, with many hundreds or even thousands of solar masses, can form when the universe is just 100 million years old or so. That's less than 1% of its current age. These stars will burn through their nuclear fuel the fastest, in 1 or 2 million years at most. And then their cores will get so hot they'll start turning photons into particles and antiparticles, which causes the star to collapse and heat up even faster. As we delve deeper into the mysteries of the cosmos, we discover that the behavior of massive celestial bodies isn't just theoretical. We've actually observed stars directly collapsing without a supernova, resulting directly in what could only be a black hole. But that's only the start of the cosmic dance that unfolds. In a large cluster of massive objects primarily influenced by the force of gravity, different objects get kicked around due to these interactions. The smallest objects are the easiest to eject, while the most massive ones are the hardest to dislodge.
That's intriguing. Does this mean that there's a sort of sorting process happening in these clusters?
Absolutely. It's known as mass segregation. The heaviest objects fall to the gravitational center, where they interact and can even merge. Now imagine this scenario. Instead of having a few hundred black holes of a few hundred or a few thousand solar masses, you end up with one single black hole of approximately 100,000 solar masses or even more. Quite a remarkable thought, isn't it?
That's mind-blowing. But what's the role of these massive black holes in the grand scheme of things?
Great question. These massive seeds might play a critical role in the formation of supermassive black holes in our cosmic history. Just as massive enough stars can directly collapse into a black hole without a stellar cataclysm, it's thought that a dense and cold enough population of gas can directly collapse into a black hole, potentially without a single star as an intermediary. This idea was recently strengthened by an unexpected observation made by combining data from NASA's Chandra X-ray data and JWST. They discovered a distant, low surface brightness galaxy from around 500 million years after the Big Bang. This galaxy contains only around 10 million, maybe up to 100 million, but not more than that, solar masses worth of stars within it.
So these findings are suggesting that supermassive black holes might not need a stellar intermediary to form.
Exactly. It's a breathtaking idea that could challenge our understanding of the cosmic history and the formation of supermassive black holes. Let's take an example of a galaxy that houses an active, feeding, X-ray emitting black hole of around 9 million solar masses. With so few other stars in this galaxy, this black hole couldn't have formed from stars. However, the direct collapse of a gas cloud is a plausible theory. You see, if we assume an initial seed black hole when the universe was only 100 million years old, there's a limit to the rate at which it can grow. This is known as the Edington Limit. If seeds of several tens of thousands of solar masses arise early on, and these supermassive black hole seeds grow rapidly thereafter, there may not be any conflict with what's observed. The big issue here is that we've already observed large, relatively mature black holes in the early universe, of hundreds of millions or even over a billion solar masses after just several hundred million years of cosmic evolution. If we trace that growth back to when we need a seed to grow from, those seeds must have been tens of thousands or even hundreds of thousands of solar masses to begin with. Starting from a stellar mass seed just won't cut it. You could consider merging the black holes from a single star cluster, then bring other star clusters with their own black holes in, and have them merge as well. However, even this approach can't grow what we call an overmassive black hole, or a black hole whose mass is comparable to the mass of all stars within a galaxy combined. The existence of such a galaxy tells us that no, merging stellar mass black holes together, even in large quantities, can't be the only way we made supermassive black holes in the universe. Some sort of massive seed, more massive than standard star formation allows for, is required. By the time the universe is no more than 250 million years old, however, star clusters, streams of gas, and these seed black hole regions can indeed merge together. The relentless pull of gravity draws nearby regions into one another, culminating in the formation of these gargantuan celestial bodies we know as supermassive black holes. Now, gravity is a force that truly favors the overdog. As time passes, tens, hundreds, and even thousands of these initial early clusters can merge to form larger galaxies.
So it's like these celestial structures are participating in a cosmic consolidation, right?
That's a great way to put it. The cosmic web causes structures to merge together into ever larger ones, particularly in the early stages of the universe. But black holes don't just grow by merging with other black holes. Anything that gets too close, be it stars, gas, dust, star clusters, or even planets, is at risk of being consumed by a black hole.
So black holes are like the ultimate vacuum cleaners of the cosmos?
Hey, well, you could say that. If anything comes too close, the black hole's tidal forces will tear it apart, forcing it into a stream, flow, and even an accretion disk around the black hole. And remember, gravity is a runaway force. The more mass you have, the more mass you attract. Some matter falling into a black hole gets heated and accelerated, emitting what are known as quasar jets. But a good chunk of that mass falls in, causing the black hole to grow even further.
Wow, that really puts the power and influence of gravity into perspective.
Exactly. If there's one term astrophysicists who study the growth of objects via gravity wish the general public understood, it's nonlinear. When a region of space is denser than average, it preferentially attracts matter. The denser you are, the more attractive you become, so to speak.
So it's a kind of gravitational magnetism where the denser you are, the more you pull in.
Precisely. It's this nonlinear nature of gravity that plays a key role in the formation and growth of black holes. Once you reach a certain threshold of being about double the average, you become much more than twice as effective at attracting other matter. When you start winning the gravitational war, you win harder and more severely as time goes on.
Can you give an example that illustrates this concept?
Absolutely. Let's take the distant galaxy Max 1149 JD1. This galaxy, whose light comes from when the universe was just 530 million years old, contains stars that are at least 280 million years old within it. Like many early galaxies, it contains a supermassive black hole that can't be explained by supernovae and steady growth alone. The most massive regions, therefore, not only grow the fastest, they eat everything around them. By the time 500 million years have elapsed, the amount of mass you've drawn into you can be enormous, just like in this galaxy I mentioned.
And these are the earliest galaxies and quasars we've found.
Yes, they are among the brightest, most massive ones we expect to exist. They are the winners in the gravitational wars of the early universe, the ultimate cosmic overdogs. By the time our telescopes reveal them, 300 to 700 million years after the Big Bang, the most massive among them already have billions of stars and supermassive black holes of many hundreds of millions of solar masses within them.
So these cosmic overdogs show significant evidence of early universe evolution.
Exactly. But don't let those who point to these pieces of evidence and proclaim cosmology is broken fool you. This is not a cosmic catastrophe. This is a piece of evidence that showcases the runaway power of gravitation in our universe. It's all part of the natural and fascinating order of things in the cosmos. Now, today we have black holes that are tens of billions times as massive as the Sun. Even at the earliest stages of the universe that we can observe, black holes with masses reaching 1 billion times that of the Sun are well within reach.
So we've come a long way in our understanding of these cosmic giants, haven't we?
We certainly have. But remember, as we peel back the cosmic veil, improved data should teach us exactly how these cosmic behemoths grew up. The study of black holes in the universe continues to be a fascinating journey of discovery.
And it's clear that this journey is far from over, right?
Absolutely. The cosmic story continues to unfold, and with every new finding, we get to understand a little more about these fascinating giants and their role in the grand scheme of the universe. So, to quickly sum it all up, scientists have been studying the early universe and the formation of supermassive black holes. These massive entities formed through the collapse of enormous stars, direct collapse of gas clouds, and the merging of star clusters and galaxies. Observations by telescopes like Chandra have given us invaluable insights into this process. Yet, as with many cosmic mysteries, the more we discover, the more questions we have. And if the universe were a movie, gravity would be the unsung hero, relentlessly pulling everything together, shaping galaxies and birthing these cosmic behemoths we call supermassive black holes.
Exactly. And that's the beauty of science. There's always more to discover, more to understand. So for all you curiosity seekers out there, remember to keep exploring, keep asking questions, and keep tuning into our podcast so we can learn and discover together. And hey, if you enjoyed this episode, don't forget to blast that like button, drop a comment, and share it with your friends. Spreading knowledge and curiosity is a team effort, and we appreciate all your support.
Absolutely. Thank you so much for joining us on this journey through the cosmos. We can't wait to see you in the next episode of our podcast. Until then, keep your eyes on the stars.
Goodbye, everyone.
Goodbye. I discovered this fascinating piece on the Big Think site titled, "What Was It Like When Supermassive Black Holes Arose?" penned by Ethan Siegel and published on December 29, 2023. You can find the full URL in the video description if you want to delve deeper into the subject. Now, I'm off.